is the 38th lecture, and we want to discuss cross correlation functions and their properties today. But before this, I want to review some of the properties of autocorrelation functions, because as you will see the properties, some properties of cross correlation are in drastic contrast or drastic uncertainty as compared to the autocorrelation function properties. If I recall what I did on autocorrelation, we had shown that Rx of 0 is equal to x squared bar. Rx, well, as you will see later, cross correlation functions do not have a relation like this. We also saw that Rx of tau is Rx of minus tau. This will also be defined by cross correlation. And then we proved that Rx of tau for non-zero tau shall be less than or equal to Rx of 0. Rx of 0 is always a positive quantity. Rx of tau can be positive or negative, but the magnitude can never exceed Rx of 0. And we showed that if x of t has a DC component, then Rx of tau also has a DC component, and if this component is x0, then Rx of tau has the DC component x0 squared. And then we showed that if x of t has a periodic component of the form, let us say a cosine omega t plus theta, where theta is the random variable, then Rx of tau has a periodic component with the same frequency, whose amplitude is a squared by 2, and then this will be multiplied by cosine of omega tau. I want your attention from that corner. All right. What we have not said last time is that if x of t has no DC component or no periodic component. You see, obviously if x of t has a DC component, then Rx of tau shall always have x0 squared. All right. In Rx of tau there shall always be a non-zero component x0 squared. If x of t has a periodic component, then it shall always have this periodic component in it, irrespective of the value of tau. If x of t has no DC or periodic component, then it is true that Rx of tau limit tau tends to infinity goes to, what do you think it should go to? 0. Why? Because when tau is very large, that is T1, there should be no correlation. The similarity is, if any, is lost as tau increases, and therefore this is a common sense, from common sense argument it follows. It can also be proved rigorously, which we shall not do here. This property is important, that when tau increases to very large values, the autocorrelation coefficient tends to 0. We next consider how to measure the autocorrelation coefficient, measurement of Rx of tau. Obviously, the measurement of Rx of tau requires a knowledge of the joint probability density function, JPDF, which is usually not known in a given situation of communication with random time functions, or random time functions imposed in the form of noise on otherwise a deterministic process. You require a knowledge of JPDF, which is usually not known, and therefore what is done is either you establish that the process is ergodic, or you assume that the process is approximately ergodic, and then what you measure is Rx of t, Rx of tau, that is the time autocorrelation function, which as you know is given by limit t tends to infinity minus t to plus t 1 over 2t, yes, x of t plus tau dt. Now, how do you measure? All right, we agree that we cannot measure Rx of tau because over the ensemble average, because we don't have a knowledge of JPDF. All right. So what we say is we assume that the process is ergodic. We either establish or assume that the random process is ergodic, so that the time averages shall be the same as the ensemble averages. Now, in order to be able to measure the time average, obviously the time interval that you have to consider is infinite. Now, you cannot go on measuring measuring things over infinite period of time. So, necessarily capital T has to be restricted. All right, capital T has to be finite if you have to measure it. All right, capital T has to be finite. Then the question arises, you measure over an interval capital T, let us say 0 to capital T, what should be the value of tau? Obviously, tau is a finite quantity. In this definition, capital T goes to infinity, but tau is a finite quantity. Therefore, tau is always much less than capital T, where capital T goes to infinity. This property that tau is much less than capital T must also be true in the measurement, in the actual measurement with capital T finite. In other words, tau must be very small compared to capital T. Only then the result shall have some similarity with the actual time autocorrelation coefficient. These are matters of approximation, and life is in general a matter of approximation, isn't it? So, what you do is the following: you measure Rx of tau, which is now look at the way actual measurement convention is. You measure from 0, not minus infinity. You cannot go to minus infinity. You cannot go to minus t either, because in any actual measurement you start at a certain instant of time and measure over a certain interval. So, you go from 0 to not capital T, but t minus tau. Tau is specifically shown here. This is a convention, an IEEE established convention, but there is a reason also, and then you divide by t minus tau. All right, x of t plus tau dt. In other words, if this is your interval 0 to capital T, then all that you can measure is autocorrelation coefficient for a value of tau, where tau is much less than capital T. And in practice, for this measurement to reflect the autocorrelation coefficient, tau is to t must be at least 1:2000. If you want to measure tau for 1 millisecond, your measurement interval must be about 2000 milliseconds. Now, if the process is ergodic, it is also stationary, and therefore it doesn't matter where your time intervals are. Your t1 could be here and t1 plus tau could be here. What matters is the difference between the two samples, xt and xt plus tau, the time instant difference. And this is the law, that tau is to t should be, it's a rule of thumb, one has to obey this, is to be at least about 1:2000. You also know that in practice we do not carry out integration, that is, we do not record the two waveforms and then multiply the two point by point, and then we cannot do that. What do? We discretize. Any integration that we have to do from practical waveforms, we discretize. That is, what we do is this interval 0 to capital T we break up into small intervals. Let us say delta t, 2 delta t, and so on. And suppose capital T is capital N delta t. Then the autocorrelation function, the time autocorrelation function at tau, where tau is, let us say, n times delta t. Tau is n times delta t, where small n is an integer, is therefore measured not as an integration but as a average over a summation, that is 1 by capital N minus small n. This corresponds to capital T minus small t. Then summation x k x of k plus n for k going from 0 to capital N minus n. This is the analog of the integration that I wanted to perform, that is 1 by t minus tau, integral from 0 to t minus tau, and the product of the two, this dt cancels with delta t that we shall have here, n minus n delta t, and this is the formula that is used for computation, and it can always be programmed on a digital computer. It is a very small, very elementary and trivial program.
What is the reason for the convention n minus n and t minus tau?
Oh, what is the reason for the? This is to bring into focus the fact that tau must be much less than capital T. If you only write capital T and capital T here, one may not remember this, but when you make tau, T minus tau, this I'm sorry, I should bring it over here. When you write T minus tau, you must remember that this must be approximately equal to capital T. This is only a reminder, a convention to similarly in the discrete computation also this fact is put into effect, that is small n, this integer may be 1 or 2, then capital N must be about 2000. If small n is 2, the capital N must be 4000. Alright. Usually capital N, if you are doing it with a digital computer with a do loop and going on accumulating, there is no problem. Capital N lies between 5000 and 10,000. And then small n typically never exceeds 50. That is, if you take 10,000 intervals, the tau at the most can be 50 times that interval. 5. Well, 5 to 10. All right. Depending on the number of samples. 1 is to 2000. No. 3 to 5. 2 to 5. 3 becomes 6000. All right. Is that clear? 1 is to 2000 is a kind of a thumb rule that one has to obey.
Should be 3 to 5.
Why? 5000.
2 becomes 4000.
It can be less than 2. Less than 2, but it can be 3. If it is 3, then 3 times 2000 is 6000, which is greater than 5000. If 5000 is the number of samples, okay. Now, there is nothing sacred about it. You might even go to 3, but then your accuracy shall suffer. Finally, we come to cross correlation function. Now, the concept would become a little more involved with cross correlation, because cross correlation function by definition is the correlation between samples taken from, between random variables taken from two different processes. That is, let us say x1 is equal to x of t1 and y2 is equal to y of t1 plus tau, and we assume that the two random variables are jointly stationary. What does this mean? x1 and y2 are jointly stationary. What does it mean? It means that the probability density function of x1 and y2, the joint probability density function, in the autocorrelation also we require a joint PDF, isn't it? In cross correlation also we require a joint PDF. The only difference is that the two random variables are taken from two different processes. One is an x of t, the other is an ensemble of y of t. And the joint probability density is denoted by p x1 y2. If the two processes are jointly stationary, then small p x1 y2 shall be independent of t1. That is right. Independent of, well, not necessarily t1, time origin, let us say t0. Which means that the correlation function if we define a correlation function between x1 and x2, this shall be independent of t1, it shall only depend on tau, and therefore we can define for this particular case of jointly stationary random variables, we can define r x y tau as the expected value of x of t and y of t plus tau, where the absolute the value of small t is unimportant, all right, which means that this is equal to x t y t plus tau p x y, the probability density function, multiplied by d x dy minus infinity to infinity minus infinity to infinity, all right. This is the definition of the cross correlation function between two random variables x and y. Obviously, yeah.
So what is the physical interpretation of cross correlation function?
It's no more concrete than autocorrelation. It also determines the same thing, that is how close or how similar y2 is to x1.
Instead we can take as y of t instead of taking y of t plus tau.
Oh, at the same instant of time, yeah. We will consider that also. That obviously is a special case of this. That would be rxy of 0. All right. Yeah, we can do that also. This is more general. Okay. Obviously now, if I interchange x and y, that is yx tau, let's see what the definition is. This would be minus infinity to infinity, y of t, x of t plus tau, p. Now comes the question. The probability density function may not be the same. Pxy may not be the same as Pyx. They may not be the same unless the two random variables are statistically independent of each other. We'll, pardon me? Why not same? The probability density function of the joint occurrence of x and y, where x.
So what's the difference between pxy and py? They're the same thing, sir.
This is not the same thing. They are different. Alright, we'll come to why they are different a little later. Alright, Pyx dx dy. If these are not the same, if Pxy and Pyx are different, then obviously Rxy tau and Ryx tau are not necessarily equal. Rxy tau is not necessarily equal to Ryx of tau. In fact, we will establish remarkably surprising relationships between the two a little later. The probability density functions are not necessarily equal. Px1 y2 is not necessarily equal to Py1 x2. We'll come to this a little later. Similarly for the time cross correlation functions, we can have ensemble cross correlation functions over the ensemble. We can have time cross correlation functions also, that is, we can define Rxy tau as equal to 1 over 2t integral minus t to plus t xt y t plus tau d tau, limit t tends to infinity, all right, exactly like the time autocorrelation function. We can also define Ryx tau as limit t tends to infinity 1 by 2t integral minus t to t. Now we can take yt x of t plus tau d tau and in general these two are not equal either. Rxy tau is not equal to Ryx tau. But for jointly ergodic process, if the two random variables are jointly ergodic, then the time autocorrelation will be the same as cross correlation, that is Rxy tau is equal to Rxy tau, and similar is the case if the subscripts are interchanged, that is if this is made Yx, then this should also be made Yx. Alright, is the definition clear? The reason why the probability density functions are not identical shall be clear later as we go ahead with the derivation. Can I go to the next term? Well, we discussed some properties, and you will see that these properties are quite different from those of the autocorrelation function. For example, Rxy0, as Pankaj pointed out, what is the relation between Rxy0 and Ryx0? Are they equal or no, not equal?
They are equal.
They are equal because xt, expected value of the product xt and yt, alright, they are equal. In the autocorrelation case, this had the physical significance of mean squared value over the ensemble. Here there is no physical significance, no particular physical significance. The only thing we know is that the changing of the subscripts does not change the value, no particular physical significance. What can you say about this Rxy tau and Rxy minus tau? If you take the definition, let me go back to the definition. This is Rxy tau. If I change tau to minus tau, then I shall have xt and yt minus tau.
Or Yx tau.
Pardon me? Are they equal? Rxy tau and Rxy minus tau? No, they are not equal. Okay. So they are not in general equal, and therefore Rxy tau necessarily, they are not necessarily equal, and therefore Rxy tau, unless Rx tau is not necessarily an even function of tau. Alright, in the autocorrelation case it was an even function. A remarkable property is that Rxy tau is the expected value of x, let's say t1, y t1 plus tau. Alright, now suppose I take the expected value of x t1 minus tau. Alright, I change the time reference so that t1 now becomes t1 minus tau. Then y, argument of y shall be simply t1. Don't you see that this is the same as the expected value of y t1 times x t1 minus tau, which means that it is equal to r yx of minus tau. Now this change, should it affect the cross correlation function? Should it affect the expectation? If the two processes are jointly stationary, obviously a change of time reference should not affect, and therefore this must be equal, which establishes the property that Rxy tau is equal to Ryx of minus tau. Can you see now why the probability density functions are different? What is the common link between them? It is Pxy and Pyx. If these two, if Pxy and Pyx were equal, obviously for joint stationarity, the two cross correlation functions should also have been equal. There is nothing else in them. Isn't that right? On the other hand, we prove.
You have xt and yt plus tau, on the other hand you have yt and xt plus tau.
So in one case yt is delayed and
So if you look at the time correlation function, we get to
Then we
can appreciate it in a better way.
even here we are assuming that the two probability density functions are same.
Saying we don't have any p function in the time domain, in the time correlation function.
yes, that is correct. So
Even then we get this result.
which result?
R xy tau is equal to r minus
yx of minus tau. Yeah. If the processes are jointly ergodic, then we can replace this by time autocorrelation. But this is an indirect argument. This is not a direct argument. Time autocorrelation functions are different. That means Pxy and Pyx are different. That is it. Well, we will continue this agony for a little while more. Why they are different. Then Rxy tau, you remember that Rx of tau was maximum when the argument was 0. That is, Rx of 0 was the maximum value of Rx of tau. Here, Rxy of tau is not necessarily maximum at tau equal to 0. But it is true that Rxy tau, but it can be shown, we are not proving this, it can be shown that Rxy tau mod is less than equal to square root of Rx of 0 and Ry of 0. That is, if you take the mean squared value of the individual processes, multiply them out, alright, take the square root, then this is greater than equal to this. But the maximum, obviously this is the maximum value, alright. The maximum value does not necessarily occur at tau equal to 0, alright. Maximum value is this, Rxy of tau is always less than this. Similarly, Ryx of tau.
So will it necessarily reach this value?
Will it necessarily reach this value? Yes, it will. It will reach this value. The maximum does not necessarily occur at tau equal to 0, but the maximum value is this. This is why less than equal to. Alright. Now, if x1 and x2, if x1 and y2 are statistically independent, then obviously Rxy tau would be equal to, which is the expected value of x1, y2. If x1 and y2 are statistically independent of each other, then obviously this will be Ex1 multiplied by Ey2. That means it will be simply x bar and y bar. And you see, it doesn't matter whether I take x first or y first, and therefore it will be the same as Ryx of tau. Alright? And the more interesting thing is that if one of the processes is a zero mean process, alright, then Rxy tau shall be identically equal to 0 for all values of tau. This never happens with autocorrelation. Alright? If one of the processes, for statistically independent processes, if one of them is zero mean, one or both, one suffices, then Rxy tau, that is the cross correlation coefficient, is absolutely 0. What does it mean? That the two waveforms of x of t and y of t are absolutely dissimilar. They are perfectly uncorrelated. Question is now, is the reverse true? Suppose I have Rxy tau equals to 0, and in addition x bar is equal to 0. Does this imply that x1 and y2 are statistically independent? In general, the answer is no. The answer is no. One must be very careful. One can get trapped in this kind of an argument. You see, this is only if statement, not only if. In other words, Rxy tau, if x1 and y2 are statistically independent, then Rxy tau is Ryx tau is the product of the two mean values over the ensemble. But if this is 0 and one of them is 0, the x1 and y2 are not necessarily statistically independent of each other. A counter example perhaps we shall construct during the tutorials. We next consider sums of random processes, that is, random processes which are generated by linear combination of two or more random processes. Alright, for example, if we have a random process, let's say x and y, two random processes, then we can generate a third random process as a linear combination, maybe sum of the two or difference between the two. So we can have x plus minus y. This can be my third random process, new random process z. Then it makes sense to talk about the autocorrelation coefficient of z, right? We are creating a single random process out of two. It can be extended to more than two, that we shall consider later. But if we consider a random process z, which is derived as a linear combination of x and y, alright, we have taken the simplest linear combination. In general, it could be alpha x plus beta y, where alpha and beta can take any values. Alright, let's consider the simplest one, which is the sum of the two or the difference between the two. And let's define two random variables, z1, which is zt1, which is x of t1 plus minus y of t1, and another random variable z2 from the same process, which is z of t1 plus tau, which is x of t1 plus tau plus minus y of t1 plus tau. Alright, then it makes sense to talk about the autocorrelation coefficient of z, the autocorrelation coefficient of x, the autocorrelation coefficient of y, then the cross correlation coefficient of x and y. There are two of them, rxy and ryx of tau. Alright, what we would like to know is what is the relationship between all these five quantities. And it's very simple to derive this. Let us see. Rz of t, Rz of tau, the autocorrelation coefficient of the process z, is the expected value of z1 multiplied by z2, which is the expected value of xt1 plus minus xy t1 multiplied by, running out of brackets, x of t1 plus tau plus minus y of t1 plus tau. And if you cross multiply, you see that xt1, when it multiplies xt1 plus tau, the expected value shall be simply rx of tau. Is that clear? When this multiplies this, two x's, you simply get rx tau. Then when plus minus yt1 multiplies plus minus yt1 plus tau, the sign is plus, plus into plus makes plus, minus into minus makes plus, and then what you get, the expected value is simply ry of tau. Alright. Then when xt1 multiplies yt1 plus tau, what do you get? rxy tau with a plus minus sign. If this is plus, then the product is plus. If this is minus, then the product is minus. And similarly, when yt1 multiplies xt1 plus tau, you get plus minus ryx tau. Alright. Now, this formula, you see that the autocorrelation of the z, the third random process, new random process, is the sum of the autocorrelation functions of the individual random processes plus algebraic sum of all the cross correlation coefficients. And this is in general true. That is, if z equal to, let's say, how do I denote this?
X plus y plus.
Okay, I would say x a, x b, and so on. And so on. That is a number of random processes. Then rz tau is the sum of all autocorrelation functions, all SCFs, plus sum of all cross correlation functions, CCFs, plus minus. This has to be the algebraic sum. Okay, this in general is true. what we proved for by taking two functions now could be extended to multiple number of functions, and you can also now introduce the scaling factors. If you so desire, you can say alpha A, alpha B, and so on. These will reflect in the corresponding additions of cross correlation and autocorrelation functions. And this is a very important application, and this is what we shall talk about now. A very important application. Suppose you have very large noise, and a very tiny signal, and the signal is periodic. Okay, so what you have is a signal x of t, which is of the form a cosine of omega t plus theta, where theta is a random variable. All right, theta is a random variable distributed uniformly over the interval 0 to 2 pi as usual. In other words, x of t is a deterministic random process, and it is mixed with a noise y of t. Let's say n of t. No, let's consider it y of t. Y of t is noise. Y of t and x of t and y of t are uncorrelated. This is quite simple. They are usually so. X of t is a tiny sinusoidal signal immersed in an ocean of noise. Let's say, you know what is Rx tau? If x of t is a periodic function like this, what is Rx tau?
A squared by 2.
A squared by 2
Cos omega tau.
cosine omega tau. Okay. Y of t, the noise component, usually the autocorrelation function of noise, Ry tau, usually it decays with tau. In other words, and this decay can be modeled very accurately by an exponential process. All right, let's consider that this is of the form, let's say y 0 squared, let's say, e to the power minus some constant alpha mod tau. That is tau, positive or negative, it doesn't matter, it decays exponentially. Now, if I mix these two processes, which means that I have a signal z of t, I have a random process z of t, which is x of t plus y of t, then we have created a new random process, and z of t, which consists of a superposition of the desired signal a cosine omega t plus theta. It is a random process because theta is a random variable, and yt is noise, wideband noise. Then the problem in communication is to recover the signal from the noise, and if the signal is immersed in noise, no amplification or filtering can recover the signal. But you see, taking autocorrelation will indeed recover, because you know Rz tau, the autocorrelation of the third process will now be simply equal to Rx tau plus Ry tau. We have assumed that x and y are statistically independent of each other, that is, they are uncorrelated. Usually that is so. A wideband noise, it is nothing, no correlation with the given signal, and therefore it is simply the sum of the two. If you plot this versus tau, we have assumed that y0 squared is much greater than s squared by 2. That is, we have assumed that the signal is a tiny one immersed in an ocean of noise, and therefore y0 squared is much greater than s squared by 2. Now if you plot this, how do you measure this? How do you measure the autocorrelation function? Well, all you do is take a sample, a large enough interval, 0 to capital T, then take a small tau, which is much less than capital T, the usual process that we have discussed, and then discretize the interval, take the amplitudes and multiply and so on. That is, you measure the time autocorrelation function, and if you plot this versus tau, obviously when tau is very small, tau is nearly equal to 0, it is the Ry of t which will dominate, even though, well, not even though, Ry of tau shall dominate, and therefore you will get something like this. You see, if you plot Ry of t, it would be something like this, Ry of tau, alright, and on this shall be superimposed this tiny periodic variation. Rx of tau is simply equal to s squared by 2 cosine of omega tau. So what you will get is something like this. Okay, and then like this. So if you go sufficiently away from tau equal to 0, let's say 2000 times tau, that is, if you observe the autocorrelation over a large enough interval, then ultimately you shall be able to see the periodicity, and all that you need from here, all that you need is to determine the amplitude, and even the amplitude is not important. All that you need is the frequency, that is omega. If you know the frequency, then obviously your autocorrelation is of the form cosine omega tau or sine omega tau, it doesn't matter. All that you wish to recover is this information, that what are the frequencies contained, and this shall be true even if you do not have one single sinusoidal component. Suppose you have many, that is, you have a spectrum. The signal, as I have told you many times, a single sinusoid is useless for the purpose of communication. It carries no information unless it is modulated. Now any modulation will introduce a band of frequencies, that is a spectrum, a band of frequencies, and you have to have a band to be able to communicate, from one place to another any piece of information. And therefore if x of t contains several frequencies or a small band of frequencies, well, this band, the components can be recovered, can be detected if you observe the autocorrelation function of the new process. Well, it's not the new process, this is what you receive. Z of t is what you receive at the receiver, and you can recover the signal, the tiny signal, from the ocean of noise. This was not otherwise possible by filtering. What do you filter? If the noise dominates, then the signal is not detectable at all. There was a I'm particularly impressed by this because it has many applications in communication, and one of the PhD thesis that was written here in communications was precisely this, to recover a tiny signal from a noise, tiny signal from a signal plus noise, and he had made the hardware for this and beautifully demonstrated how it can be done. Of course, what his innovation was in the process of taking the autocorrelation. He had done this in a discrete manner, but using a very innovative concept. He used some simple differentiators for the purpose, but that is beyond the scope of this course. The point that I want to mention is that unless you introduce the concept of correlation here, this could not be. This is one of the remarkable applications of correlation. All right. The next topic in the logical sequence would be to see if random functions could be dealt with in the frequency domain. You know, in the usual functions, we have seen that Laplace transform or Fourier transform makes things very easy. Convolution becomes multiplication. Convolution in the time domain becomes multiplication in the frequency domain. And all that we have talked so far is in the time domain. Rx of t, Rx of tau, time autocorrelation function, cross correlation functions, they are all in the time domain. The question is, can we do anything in the frequency domain of this? You see, one of the difficulties is that a random time function, we are not guaranteed that it shall be absolutely integrable. It extends from minus infinity to plus infinity, and any integral that you take, it is not guaranteed that it shall be less than infinity. Even if you guarantee this for one sample function, you don't know whether it will be valid for other sample functions or not. Alright? And therefore, you cannot take the Fourier transform. Fourier transform, one of the conditions is that it must be absolutely integrable. The other condition is that its energy It's either a finite energy or finite power. The other condition is that its energy is finite. Can you guarantee that? You cannot. You cannot guarantee because the function is random. It is unpredictable and it extends from minus infinity to plus infinity. So what do you do to be able to transform? On the other hand, we are very tempted because of our experience with non-random time functions. We are very tempted if we could bring it to the frequency domain. So the only thing that we do is, if I have an infinite length of rope, all right, and I want to see, I want to at least estimate its properties. What do? My field of vision is limited. I cannot see infinity, from minus infinity to plus infinity at one go. So what do? I take a part of the rope. All right. If somebody wants to sample the IIT students, well, he cannot go and interview 1300 students. What he does is he takes several representative samples from, let's say, 205, takes some from 344, and so on and so forth. So sampling. Here also we do the same thing. This is an artifice that we do. That is, we have the time function from minus infinity to plus infinity. We allow this time function to go through a window, a finite window, from, let's say, 0 to capital T. And then, since the function has now become limited in time, it is possible to satisfy the Fourier transformability condition. All right, a finite time signal, not necessarily, because there might be infinite number of infinite discontinuities. So we say that within the window the time function is well behaved. We assume, and then we allow capital T to go to infinity. That is, after taking the Fourier transform, we allow capital T to go to infinity. No, we cannot. As soon as we do that, we violate the condition of existence of Fourier transform. But what we assume is that the random time functions are always judged in terms of their statistical averages, that is, expectations. All right. So one is Fourier transform of the window time function, which integrates things from minus infinity to plus infinity, integrates with respect to t, and the expectation integrates over the ensemble, right? What we do is, we first take, now listen to this carefully, this is an artifice that we employ, but it does give results. So for an engineer, whatever works is wonderful, all right? We don't care if it has violated some of the fundamental principles or not, if it works. What we do is, the process basically is, we cannot take Fourier transform of a random time function because Fourier transformability is not guaranteed. We guarantee this by passing the time function through a window. In other words, we take a sample, a very long thing, we take a sample of it. And then what we do is, we Fourier transform this and also take the expectation. And then we interchange the operations. Expectation is over ensemble and integration is over time in taking Fourier transform. So we first take the expectation and then take the Fourier transform. You understand what I mean? In the process, you will see that it is possible to get a meaningful quantity in the frequency domain. Obviously not the spectrum, because Fourier transform x of t doesn't exist. What we can obtain is an expression for spectrum density. You remember Parseval's theorem, integral 1 by 2 pi, integral x of omega magnitude squared d omega, and x of omega squared was spectral density. We will see next time, tomorrow, that it is useful, it is possible to introduce the concept of spectral density in the context of random time functions also. That's all for today.